Okay, so in the last class we have been talking about this frequency response, right? When we spoke about this time response, we used an S plane and then we analyzed that the output y of t will have two components, right? So one is natural response, the other one is the forced or steady state response. So when I speak about this frequency response, what is that we are really concerned? Am I really worried about this natural response? No, right? Because what we know is, in general, the natural response would die, okay, provided if I have the poles on the half of the S plane, okay, so they eventually die. So I'm not worried about this natural response at all, okay. So what I'm really worried is the steady state response in my frequency response. And we also spoke that this steady state response is purely from the poles of the input function, okay. So this is what we finally concluded, and what we did is like we tried to discuss about the frequency response by having some sort of gain, okay, where there is no pole, and what we tried to do is like I had a signal which is having a single frequency, and what happened is like I would get the same single frequency at the output, like whatever the frequency that I feed in would appear as an output with same frequency, but what would change between the input and output is so there are only two things that would change. One is the magnitude, okay, the second one is the phase, okay. So there will be these two changes that would happen, but the frequency won't change between the input and output provided the system is an LTI system, okay. So these are some of the things that we discussed, and later we were trying to plot the Bode plot. So we were trying to plot these two things where we had this x-axis to be log of omega, and for the magnitude plot what I took was the magnitude of my system and then the phase angle of this, okay, so in terms of degree. So these were some of the things that we discussed in the last class of our thing. What we did is like we just looked into some transfer function and then we spoke like how to draw this in terms of magnitude and phase plot. Am I right? So what we did is like we just took each of these elements in the transfer function and we try to analyze how does it react with respect to the frequency, okay. And I just want to make a final conclusion from here is that whenever I have a zero, what type of magnitude plot that I would get? Will it be a straight line horizontally or without any slope or with slope? Okay. Yeah. So let us take this particular simple case where I'm concerned about only this particular part of my transfer function. Okay. So what we did is like we just try to map this S to j omega. Okay. And after then what we had is something like this. Now for this I just want to have two type of plots. One is the magnitude plot, the other one is the phase plot. Now how do I draw this magnitude plot for this? So again I have to take this in terms of j omega, and I'm going to assume that at a time I have only one transfer function or only one part of my h of s, okay. Yeah, so first of all I need to identify the zero. So let us assume that I have a zero somewhere over here, okay. So now what happens is like this is going to be in terms of dB. So for frequencies that is lower than this Z1, I'm going to assume that this particular part is going to be a negligible, okay. So in turn what is my H1 would be just 1, okay, and if you take 20 log of 1 it would be obviously 0, right. So I start drawing like this, and I'm going to talk about only the asymptotic behavior. I'm not going to exactly draw like it actually makes a curvature, but I'm not going to discuss that, okay. And the moment I reach here, so what happens the moment I reach to Z1? Yeah, so what happens is like in the previous case for frequencies that is lower than Z1 this was negligible, right. For omega that is lesser than Z1 we assumed that it's supposed to be negligible, but right now I'm talking about a frequency which is greater than Z1. So in a way that this particular part would become negligible, and what I have is something like this j omega by z1 is the dominant one. Okay, so this becomes a dominant term out of this 1 and j omega term. Now let us try to plot this. So what I do is like I approximate this h1 of j omega for omega that is greater than z1 to be approximately equal to z1 magnitude. So it would be something like a term something like this, right? Am I right? Okay. So then again I have to multiply with 20 log of something like this. Okay. So in general you could be able to see that this y is basically a function of this log of omega. Okay. So what I have is something like y equals to mx, and this log of omega is a term that is related to my x axis, right? So I have to draw a line which has a slope of 20 dB per decade, right? So this is the reason why we draw this line after this z1 with having a slope line of plus 20 dB per decade. Okay. So again the decade comes just because I've taken the logarithmic scale for my x axis, and that's the reason why we write this per decade. It's all fine? Okay. So now let us talk about this phase angle. Now let me map my 0 degree somewhere here. Okay. Now how will I evaluate the phase value of this particular transfer function? Let me label them as h1 and as phi1. Okay. So it's basically tan inverse of some imaginary part of my transfer function divided by the real part. Okay. So in this case the imaginary part sits here. So this is my imaginary part and this is my real part, right? So what I would get is something like omega by z1 divided by 1, and this is what I would end up for. So right now when my frequency is less than say for example or equal to less than or equal to 0.1 times that of z1, I can assume that this value that I would have under this tan inverse is approximately equal to 0 itself. Okay. If that is the case, what is my tan inverse of 0? It would be 0, right? So for frequency right from 0 to all the way to 0.1 times that of z1, I will have the 0 phase. Okay. Now when I have a frequency which is exactly equal to z1, what happens is this I just substitute this z1 here and the value will become something like tan inverse of 1. So what is this tan inverse of 1? Yeah, it would be 45 degree. So now from here on, when I am at z1, I have to map this to 45 degree. So I'll just continue drawing a slope with a line, okay, which runs at 45 degree. So now what happens the moment I increase the frequency somewhere which is equal or greater than this z1? What I can do is I can approximate this tan inverse of 10, where 10 I can assume it's a quite larger value, and we can approximate this value to be around 90 degree. Okay. So once I reach to a frequency which is 10 times greater than this z1, what happens is like the phase value would attain its constant value of 90 degree. Okay. So this is what we were trying to discuss in the last class. Okay. So when we discuss about 0, like this is the relation that we had. And what about the pole? Say for example I have this h2 of j omega, where I have 1 upon j omega p1 plus 1. Now what changes I need to do across the magnitude and the phase plot? What happens the moment I reach, say for example in the place of z1 I have this p1. Okay. So what happens after then? It would decay at a rate of minus 20 dB per decade, and the whole of this particular line that I have drawn will go in the negative axis. Okay. So when I have a pole, this will induce a maximum of minus 90 degree phase shift. Okay. When I have a 0, this will induce plus 90 degree phase shift. Okay. Is that is clear? And again the magnitude would get degraded something like this. Okay. So you would get something like this in the place if I have this p1. Yeah. So these were some of the things which I really wanted to talk, and today I just want to really talk about certain things. What did I say when I begin this particular class? I said this frequency response is a study about steady state response. But which poles and zeros I am talking here, at which the slopes are getting changed? Yeah. So those are the system poles and zeros I am talking. Is that clear? So even though the frequency response is a study of steady state response, for which the input function plays a major role, the poles in my system or the zeros in my system would modify those behaviors. The modification is something like this, okay? So where I had a straight line and after then the slope gets changed. Is that all clear? Now I just want to talk with respect to an S-plane, and let us assume that there is a single pole P1. Okay, I just want you to draw the magnitude and the phase. Okay, so both are log of omega, and let us assume that I have a system. You see, for the given system, I have drawn already the S-plane, but I just want you people to draw the magnitude and the phase. Okay, so let me call this as h of s, so that I can map here as in terms of dB, and then h of j omega in terms of angle. How do you begin doing it? So since I have given this factor k for frequencies that is lesser than P1, what happens is I would get something like, okay, and the moment I reach this P1, now whatever I mapped here is my system pole, but I also know that the input also has a pole, right? Input is a sinusoidal input that also has a pole. Now how will I map that particular pole? Say for example I am working at a particular frequency. Can I map onto my S-plane? Because for a step input, what we did is we mapped this pole to be exactly at the origin, but right now I don't have a step input. Okay, so how will I map it, and how will I can relate things that I have across these two things? So this was for a step input 1 by s. So we fixed our pole for a step input at the origin, but as of now when I talk about the frequency response, I'm not really working with my step input, but rather a sinusoidal input which varies with the frequencies. Okay, so now let us assume that I have a particular frequency, and let me mark this as j omega 1. Okay, now for this, at this particular frequency, if at all, if I want to evaluate the magnitude, how would I do that? Actually it is possible, but the point is, like we have also discussed about the S-plane. What is the drawback with this S-plane? I will not able to get the information about the DC gain, or the factor k that I have plugged in here is not really visible, right? But still we can actually work, but I will just give you a overview. Like I just want to give you a qualitative view, not a quantitative view, right? So the magnitude is nothing but is the vector that is pointing from P1 to the frequency at which you are working. Okay, and that exactly replicates your magnitude plot. But what about the phase value? How do you map that? So again you have a real and an imaginary part, right? This particular line. So what happens is the phase value would be like whatever you're reading as a phase difference. Okay, between this line and this line, this is the phase angle that you actually read, and you will try to plot it here. Okay, so I'm just teaching this for a particular reason. Okay, so this is what would happen. And now what if I'm trying to increase the value of my frequency? I'm working at omega 2 somewhere here, j omega 2. This is my new frequency. So how would you find the phase value and the magnitude of it? So you have to again draw a vector that is pointing from this P1 to the new frequency component omega 2. Okay, but you know that this is a pole, and the magnitude, say for example I've taken this magnitude to be equal to Q2, and the previous one was Q1. Okay, But how will I translate this in terms of magnitude? Okay, so this is the information that I've got it from some MIT course. Okay, so the magnitude would be something like k by q1, where the q1 is nothing but the distance from here to here for a frequency that is equal to omega 1. Okay, and now when I change the frequency to omega 2, then the magnitude actually changes something like this. Is that is all clear? And if it is a 0, then you need to multiply k times that of whatever the magnitude of your vector that is pointing. Okay, so for 0, let me assume that it is r1, so it becomes to the top. These are my poles. J omega is nothing but the pole, right? Because no, just a moment. Yeah, so these were the poles, right? What we did is, like, we try to analyze this, and we got down to this particular expression where S equals to j omega, the other one is S equals to minus j omega, or right? So I'm just working with one single frequency component because the frequency will be always in the positive axis, so I just work with it. Now as I vary this, what is happening to my system is what I'm trying to measure. Okay, so this is just a qualitative view. Now I just want to put a question. What if I have a complex conjugate poles? Okay, say for example I have, how will I evaluate the magnitude and the phase? I have two frequencies. One, first we'll talk with J1 and later we'll talk about J2, and let me take off this, because since I have two poles. Is the question is clear what I'm asking? Yeah, so how will I evaluate the magnitude plot? I will not talk about this P1. I guess it would be because both have the same real part, okay, and they are complex conjugate. So I will have two poles sitting on one over the other, something like that, okay. And the value of it is basically the square of real and imaginary is what I believe, but I'm not pretty sure, okay. But let us assume that there is a pole and that is sitting here, okay. Now the question is, how do I evaluate it? So now again what I do is, I take this and I take this, okay. So let us label this one as Q1 and Q2. Now for a frequency that is equal to omega equals to omega 1, then what happens is I would have k divided by Q1 into Q2. Clear? Now what would happen for a frequency that is closer to my omega 2? Yeah, obviously this distance would get reduced, but this distance would get increased. But effectively what happens is, there are certain cases when this pole is a bit closer, okay. When these two poles are a bit closer to my imaginary axis, what happens is, like, this term would become lesser than 1, okay, or the magnitude of it would become lesser than 1. When you divide something, k divided by a quantity which is lesser than 1, what would happen to the total value? It rises, right? So eventually at this omega p1 there will be a rise and then it goes off. Can you relate something? What happened for us when I had a complex conjugate pole for our transient response? We discussed about such kind of response for a time. For a step input, what was our time response? Do we had something like this? Is this our graph that we had for a complex conjugate pole? Or this is the graph that we had got? Which type of graph that we had when I had a complex conjugate pole? Yes. So it was a sinusoidal, but the point is, it was something like this, right? So there was an exponential as well as sinusoidal, And the same thing happens, some kind of phenomenon happens even here. You see, when the poles are complex conjugate, there are two things that happens, one in time domain and the other one is in the frequency domain. Okay? In the case of frequency domain, what is happening is there is a peaking that happens in my magnitude plot. Okay? Exactly at my system pole location. Similarly, there happens to be a kind of oscillatory behavior with a decaying factor. Okay? So whenever the poles are complex conjugate, then there are certain things that we need to consider. Okay? So related to this, we'll discuss when we talk about stability. Okay? So you need to know where exactly my poles supposed to be, if at all, if I need to have a peaking. Now, say for example, I don't have this kind of pole location, but my P1 and P2 are real. Okay? Let us assume that I have my P1 here and I have my P2 here. Now, how would my magnitude plot would look then? For this type of pole location, how will I draw the magnitude plot? I know what is this answer for supposed to be for my y of t, but I just want to know how do you draw for my magnitude plot. How do you do that? Okay, so first of all, there are two poles and those two poles are real and they are not exactly at the same location. So what happens is, I need to have two values here. One is P1, the other one is happening to be at P2. Okay, and due to which what happens is I just try to draw a line, okay, till I reach this first pole. The magnitude is assumed to be constant, but the moment I reach this P1, what happens to my magnitude? Yeah, so it starts decaying, right? So it starts decaying at a rate which is minus 20 dB per decade, and after a while I reach to my second pole, and what happens after then? Yeah, so it goes at a rate of minus 40 dB per decade. Okay, so similarly, let us try to evaluate the phase. Okay, so I'll just go with and 0.1 times that of P1 here, okay, and 10 times that of P2 and 10 times that of P2. Okay, yeah. So how will I draw the graph for the phase? So I know that a single pole will induce a maximum of 90 degree phase shift. Okay, and I'm going to assume that this P1 and P2 are placed so far away. Okay, so they will not talk with each other. So if that is the case, what happens is the pole P1 alone would actually have created a minus 90 degree phase shift. Now, when I encounter this particular part, okay, throughout this entire region, there is already a phase shift of minus 90 degree. And then when I enter into this 0.1 times that of P2 to P2, what happens to the phase? Again, it starts decaying. Now, exactly at this particular location, what would be my phase value? Minus 135. Okay, and then the moment I reach to 10 times greater than that of P2, what happens is, what is the maximum phase value that I would get? It would be minus 180 degree. Okay, so I can even prove the same statement with respect to the tan inverse term. Okay, so this is my phase angle, and I generally have tan inverse of, so minus tan inverse of this omega times that of P1 minus tan inverse of omega times that of P2. Okay, so let us look across each of these frequency component and let us try to approximate the values. Okay, now for omega, that is less than 0.1 times that of P1. Okay, what happens to the first term? So here again it is 0.1 times that of P1, so I generally have a value that is closer to 0. So the phase angle that is induced by the first term is 0. What about here for this second term? So again, when I substitute, what happens is the ratio will obviously be far lesser than this 0.1. Okay, so again this term will again induce a 0 degree. Okay, so totally there is a phase shift of 0 degree for frequencies between here to here, okay, between these two locations, what happens is the phase value would retain to be a value of 0 degree. Now when I have omega that is equal to P1, again I just plug in those values, okay. So here the ratio becomes 1. So now tan inverse of 1 is basically 45 degree, but what happens over here? We know that the value of P1, or in general the P1 is much smaller than the value of P2, okay. So again the ratio of P1 by P2 is approximately equal to 0.01 or something, okay. So again what I know is from here I would get 45 degree, from the second term I just get 0 degree. So the total phase shift would be just 45 degree. Now similarly for omega that is equal to 10 times that of P1, again I would get something like 10 here, and then tan inverse of something like 0.1 here. Now this 10 we can assume it's an infinite quantity, and then I can approximate this to induce a 90 degree phase shift, whereas the other location is inducing just 0 degree, okay. So a total phase shift of 90 degree. Now when I have frequency that is P2, then again the phase value is nothing but tan inverse of something like 100, and here tan inverse of 1. So the 100 is obviously 90 degree would come, and from here it would be 45 degree, and that's the reason why we wrote it as minus 135 degree, okay. Now when I work at frequency which is 10 times greater than that of P2, then both the tan inverse term would induce 90 degree and again one more 90 degree. So a maximum phase shift of 180 degree is what I would get, okay. So this is how I evaluate the phase value for each of the frequencies that I am working, and that is how I plot this graph. Any doubt in this? Okay, so there are two information that we have got here. The very first information is whenever the poles are complex conjugate, then what happens is like there's supposed to be a peaking that happens in my magnitude plot, okay. I erased it, okay, and the four poles that are complex conjugate, we had such relation, but when the poles are real, then I would get a graph which slowly varies and reaches the final state, okay, and the corresponding magnitude and the phase plots are shown here. Is that all clear?
Now let us try to understand the behavior of the step response and the frequency response of a second order LTI system. Now let us consider this particular GUI where I have a control for the factor of zeta, okay. So when the factor of zeta is equal to 0, you could able to see that the poles are basically lying on the imaginary axis, and due to which our step response creates a kind of oscillatory behavior. So you could able to see that there is a kind of sinusoidal signal that gets created when the poles are at the imaginary axis. Also, when you look across the frequency response, you could be able to see that at the frequency where the two poles are lying, you could be able to see that there is a kind of peaking that happens across this omega value, okay, where exactly the poles are lying. So it is at that particular frequency you could be able to see that there is a kind of peaking that happens in your magnitude plot, and the phase is also changed from 0 to 180 degree just because there are two poles at this particular location, okay. So there is a sharp transition that happens between 0 to minus 180 degree. So now what we do is we'll try to vary the value of this zeta right from 0 to all the way to 2, okay. So first let me enter a value of 0.5 and see how the step response as well as the magnitude of the frequency response gets varied along with the phase. So now you could able to see that the moment I enter the 0.5 as the zeta value, the poles have some real part, and due to which the step response has oscillatory as well as an exponentially decaying factor, Okay, so the oscillatory behavior happens just because of the imaginary term, and the exponential decaying factor just because of the real term. And again, you could able to see that there is a kind of short peaking that happens for a value of zeta that is equal to 0.5. Okay, and now when you look across the phase takes a transition from 0 to 180 degree, but this transition is not sharp as we had before. So there is a kind of gradual change from 0 degree to all the way to minus 180 degree. So this actually replicates what is known as underdamped condition. Okay, so with respect to the step response. Now what I do is I'll try to change the value of the zeta to 1. Now when we have 1, you could able to see that both the poles are real and they overlap one over the other. So I have two poles which are equal and real, and due to which the step response is actually varies slowly and all the way it reaches its final state. Okay, and here again you could able to see that the magnitude plot doesn't reflect any kind of peaking where the poles are located. Okay, but the rate at which this decays is obviously it is 40 dB per decay, which you can visually see it. Now let me try to vary the value of zeta to, say for example, 1.5, and now that the poles are real, but what happens is like the poles are not equal to each other, and due to which, or due to the pole that is lying closer to my origin, there is a kind of a slowly varying output for the step response. So what I really mean here is that there is a kind of lethargy in the response for the step input. And again you get able to see that there is these poles are far away from each other. So initially when I encounter the first pole, the magnitude plot degrades at a rate of minus 20 dB, and the moment I encounter the second pole, then the degradation falls at a rate of minus 40 degree. And again there is a kind of phase change which varies from 0 to minus 180 degree,